Hi, so what we're going to look at now is the reduction of carboxylic acids. Alright, so one of our stronger reducing agents is lithium aluminum hydride. And so what lithium aluminum hydride does is it delivers hydrides, so these hydrogens, over here to the base of the carbonyl. And what we'll essentially do is reduce this carboxylic acid just to an alcohol. Alright, so the nice thing about this is it keeps all the carbon framework the same, so let's just draw that. And then we're going to keep this OH and just get an alcohol, and so that's our product. If you want, we could draw out the hydrogens, and so we've replaced the carbonyl with two hydrogens, and those hydrogens were delivered from the lithium aluminum hydride, and then this hydrogen on the oxygen came from the water workup. Alright, so it completely removes the carbonyl and just leaves us with an alcohol. Alright, now let's scroll down to the bottom one. And what we want to look at is there's several different types of reducing agents. Right, so on the right, we have lithium aluminum hydride, which is our strongest. We have sodium borohydride, which when we looked at ketones and aldehydes, kind of worked analogously to lithium aluminum hydride. Right, it reduced them to alcohols, but it's a little bit weaker. And then you have hydrogenation, so hydrogen and some metal catalysts. Now, if we look at lithium aluminum hydride first, let's just draw the carbon framework. It's going to still give us that same alcohol. Right, so we're going to take this carboxylic acid and convert that to an alcohol. And so that's the alcohol here. Alright, we're going to keep the carbon framework on the bottom, and it's going to leave the alkene alone. Alright, but it's still going to reduce the aldehyde. Alright, so it'll take that aldehyde and make it into an OH. Alright, so what this does is take this aldehyde to an alcohol, and it also reduces the carboxylic acid to an alcohol, but it leaves the alkene alone. Alright, now sodium borohydride is weaker. Alright, so it will leave the carboxylic acid alone and only reduce ketones and aldehydes. So let's draw this one. But it also leaves the alkene alone. Alright, so what we've done is we've kept the carboxylic acid, right, that we had in our starting material. We've reduced the aldehyde to an OH, and it would do the same for ketones. And we've also left the alkene alone. So sodium borohydride, since it's milder, won't react with carboxylic acids, and eventually we'll see the same for esters. Now the bottom one, hydrogenation doesn't tend to affect carbonyls. So it won't affect the carboxylic acid, it won't affect the aldehyde. What it will specifically reduce is the alkene. So it's going to reduce this carbon, which used to be a double bond in our starting material, becomes a single bond. And it leaves the two carbonyls, ketones, aldehydes, carboxylic acids, esters. It'll leave all of those alone. So we keep all of our carbonyl groups and selectively reduce the alkene. Alright, so the take-home message from this is lithium aluminum hydride typically reduces any carbonyl compound. Sodium borohydride is a little bit milder, and so it works really well on ketones and aldehydes, but not carboxylic acids. Right? And both those leave alkenes and alkynes alone. Hydrogenation is really good for selectively reducing alkenes and alkynes, but not reacting with carbonyl compounds.